Welcome back to another episode of Tech Talk Today, where we explore the fascinating world of technology and the innovations that are shaping our lives. I'm your host, Yornane, and today we're diving into a critical concept in distributed systems, causal consistency, and how it relates to linearizability. If you've ever wondered how systems manage to track operations, especially when multiple people are working on the same project, you're in the right place. We'll break down some complex ideas into easily digestible pieces, so whether you're a tech enthusiast or a seasoned developer, there's something for everyone. Let's start with the basics. Picture a project where several developers are making changes at the same time. Each change, or commit, can be visualized as a point on a graph, with lines connecting them to show how they relate. Sometimes these changes happen in a straight line, but other times they branch out, creating a more complex structure. This leads us to the relationship between causal order and linearizability. Linearizability is a strong consistency model that ensures operations appear to happen in a strict sequence, preserving the order of events. If a system is linearizable, it guarantees that causality is maintained. This means if one operation causally precedes another, the system will reflect that order. However, achieving linearizability can come at a cost, specifically in terms of performance and availability. In systems with significant network delays, like those spread across different geographical locations, enforcing linearizability can slow things down. That's why some distributed systems choose to forego it, sacrificing strict order for better performance. But there's good news. A middle ground exists. Causal consistency is an alternative that allows systems to maintain causal relationships without the performance hit that comes with linearizability. In fact, causal consistency is the strongest consistency model that remains efficient even in the face of network failures. Now let's dig a little deeper into how systems can maintain causal consistency without being linearizable. One key idea here is the concept of a partial order. In this framework, operations can occur in any order, but if one operation causally precedes another, that order must be respected across all replicas of the system. When a node processes an operation, it must ensure that all causally preceding operations have been completed first. If a necessary operation is missing, the later operation has to wait. This is somewhat akin to how investigations determine the sequence of events in a crime. Did the CEO know about a critical issue before making a decision? To track these causal dependencies, systems can use techniques like version vectors. These vectors help maintain a record of which operations have occurred and their dependencies. However, tracking all read data can become impractical, especially in applications where clients read extensively before writing something new. Imagine the overhead of keeping track of every piece of data read before a write operation. It can spiral out of control. Instead, systems often rely on logical clocks, which provide an algorithmic approach to generating a sequence of numbers that can help order operations without the pitfalls of physical clocks, which can be unreliable. Now let's talk about how we can create a total order of operations that respects causality. A common method is using Lamport timestamps, introduced by Leslie Lamport in 1978. Each node keeps a counter of operations it has processed, and the timestamp is a combination of this counter and the node's unique identifier. This method ensures that every operation has a unique timestamp, allowing for a total ordering of events. When a node receives a request, it checks the maximum counter value it has seen and updates its own counter accordingly. This way, if Operation A causally happened before Operation B, the timestamp for A will always be less than that of B, maintaining the causal relationship. However, while Lamport timestamps provide a total order, they don't distinguish between concurrent operations and those that are causally dependent. This is where version vectors come into play. They can tell if two operations are concurrent or if one is dependent on the other. Yet, Lamport timestamps have an advantage. They're more compact, leading to better performance, which is crucial for systems that need to scale efficiently. As we wrap up today's discussion, it's clear that maintaining causal consistency in distributed systems is a complex but essential task. While linearizability offers a strong guarantee of order, it can hinder performance and availability. Causal consistency provides a viable alternative, allowing systems to operate efficiently while still respecting the relationships between operations. Researchers are actively exploring new database designs that prioritize causal consistency, aiming to strike the perfect balance between performance and reliability. While challenges remain, the future looks promising for systems that can maintain these crucial causal dependencies without sacrificing speed. Thanks for tuning in to this episode of Tech Talk Today. We hope you found our exploration of causal consistency and linearizability insightful. If you enjoyed this discussion, don't forget to subscribe, rate, and share with your fellow tech enthusiasts. Join us next time as we dive into another exciting topic in the world of technology. Until then, keep questioning, keep learning, and keep innovating.